afternoon today to have Kasia Jankiewicz speaking about profinite properties of Artin groups.
Thank you, Catherine. Thank you all for coming. I'm going to start talking about Artin groups. So they are a family of groups generalizing braid groups. So that's kind of a motivating example. I'm not going to draw a picture. I should have done it and draw it on the hidden board. But I think probably most people are familiar with braid groups. We usually think about them in terms of those diagrams of braids. Operation is concatenation. I'm going to write down a group presentation. So I'm just using an example of a braid group on 4 strands. So it has 3 generators where each of the generators is a braid with a single intersection. Just of 2 consecutive strands. And it's not hard to check that if we look at, for example, braids A and B, they satisfy this braid relation. Similarly, the other 2 and braids that use disjoint set of strands satisfy commuting relation. Of course, braid group, I mean, this is just one way of writing it down using group presentation. There are a lot of different ways one can talk about braid groups. You can define them in terms of like mapping class groups of punctured disks. You can talk about them as fundamental group of configuration spaces. I'm not going to talk about all of those perspectives today because I'm just going to maybe talk about one perspective that generalizes to Artin groups. So, but kind of the easiest way of defining Artin groups is also in terms of presentations, because they're always given by presentations that look like that one above, but just a little more generalized, general. So Artin groups are always given by presentations where we have some number of generators and we have all the relations that look like those, but are possibly longer. So we have any pair satisfies a relation where we have alternating word in those 2 letters of the same length, one starting with one or one with the other being equal. So in particular, this is this relation when m is equals 3. This is when n is equals 2, and you can have longer relations. You can also have no relation involving two generators. So this is a definition, but kind of more geometrically, Artin groups can also be defined as fundamental groups of certain complex or complexified hyperplane arrangement complements. And I believe this is, how they were first defined. And so maybe I'll just give you an example for the braid group, and you can kind of imagine how it generalizes. So I'll just write it here, a braid group on 4 strands. So maybe this is also something I should maybe mention here as well, that, or I'll actually just mention it here. So I say complexified hyperplane arrangement complement, where this hyperplane arrangement is coming from the action, the reflection action of a Coxeter group. So let me just explain. So for every Coxeter group, there is an associated Artin group where, we just like the Coxeter matrix, Coxeter diagram, however you like to think about your Coxeter group data kind of defines this presentation by just having generators corresponding to entries in the columns or rows in the matrix, or the vertices of your graph, and those relations Mij are the kind of standard numbers. And that Coxter group that is associated to the data is a natural quotient of this Artin group, where we just send those generators to the natural generators of the Coxter group. So all generators are of order 2, and this is the relation that is satisfied. Maybe. Let me just write the kind of Coxter group that would be associated to the same system. That's all generators of order 2, and it's maybe more typical to write the Coxter in the Coxter group presentation, this kind of second relation in this form. This is equivalent when to this type of relation when the generators are of order 2. And so specifically for braid group on 4 strands, this kind of Coxter quotient corresponding to braid group viewed as an Artin group is the symmetric group. The symmetric group on 4 elements, and there is kind of very simple action by reflections of S4 and R4, which is just action by permutations of coordinates. And if we look at transposition in the symmetric group, they act as reflections. Reflection about some hyperplane. So for each transposition, we have a hyperplane. And so if we kind of remove those hyperplanes where some of those transposition reflect about, those are the only subspaces that are fixed by some element. So this actually becomes free. That's right. S4 acts freely on that complement. This is this hyperplane arrangement complement where we have a free and proper action. And so this is the thing that we're complexifying. So it just means like we're kind of taking the same arrangement, just complex 4-dimensional vector space. And we can still consider this action. We can quotient by this action, and that's the space whose fundamental group is in this situation braid group on 4 strands. And this whole kind of example, this is quite general, modulo some details that I don't want to go into right now, but we can always start with a Coxter group acting by reflections. Those are, I guess I put those reflections here, quotation marks. They're not necessarily orthogonal reflections, but we can always think of them as reflections. We get this hyperplanar arrangement corresponding to Coxter group complexified as we are always obtaining as the fundamental group associated Artin group. And yeah, so generally, there's a lot unknown about Artin groups, kind of generally. So for general Coxter groups, there's a lot known if we start with a finite Coxter group and obtain the Artin group from there. But kind of for general Coxter groups, if we look at Artin group that is affiliated, we don't know even like very basic group theoretical properties. We don't know whether those groups, so we know those are always infinite groups. We don't know whether they ever have torsion. They don't look like they should have any torsion, like looking at presentation. We believe they don't have torsion, but it's not known in general. We don't know what their centers look like. There's a conjectural description. We don't know whether a word problem is solvable in general. So pretty much probably any question, basic group theoretic question you could ask, probably in general is not known. Okay, so this is like just a short intro to Artin groups. I'm gonna focus on profinite properties. And so, number one profinite property is residual finiteness. So let me say that a group is residually finite.
It's right angle, then we know much more.
Yeah. Yeah, so there are certain families, of course, like right-angled Artin groups are well understood. Those finite type, which means that corresponding to finite Coxeter groups are fairly well understood. There are also like class of two-dimensional ones are somewhat understood. But even, I guess, what I'm going to talk about is going to be mostly, like most of the results are just for two-dimensional ones. So this is still like things that were not known previously. Yeah, so group is residually finite if there are a lot of different ways of saying it. One is that if I take any non-trivial element in the group, then there exists a finite quotient where my element survives. So it's mapped to non-identity element in the finite quotient. Maybe like nicer way of even stating this definition is like group is residually finite. So equivalently, if it embeds in the product of finite groups. There are a lot of different ways of rephrasing this also other than those two. Let me see if I want to use any. No, maybe I'll just say about writing it. Another way of thinking about residual finiteness, or rather another way of restating it, is that a group is residually finite if I look at its Cayley graph and I look at a ball of some fixed radius, I can always find a quotient, finite quotient whose Cayley graph has ball of that radius that looks identical. So you can think of this property as being able to approximate kind of finite portions of Cayley graph and finite quotients arbitrarily well. And so it's a classical theorem by Maltsev that linear groups, or basically finely generated linear groups, are residually finite. So subgroups of matrix groups. And I guess I want to consider the question which Artin groups are residually finite. And maybe to connect it also, I mentioned there are a lot of things that are unknown. There are also like consequent, like other than in a way it's somewhat natural property to ask for as being, whether you embed in a product of finite groups, there are also consequences of being residually finite. For example, having solvable word problem, which I kind of advertise is not known in general. And so there are some families that are known to be linear, and maybe sort of first example should be right-angled Artin groups. So this is family when all the relations are just commuting relations. So there's either a commuting relation or no relation that two generators have. And finite type, which is when constant group is finite. Those are two classes that are known to be linear. I guess the linearity of finite type, it was first proven for braid groups in around like 2001 by Bigelow and Kramer, and soon after for all finite type Artin groups by Cohen, Wales, and Dean independently.
Like cases or case by case or some?
No, it was first for like braid groups, or maybe it was first for like braid group and force track braid groups, and then like all this spherical type. Because they kind of, the methods that was used to do it for braid groups was kind of generalized, like not very hard, like it wasn't very hard to generalize it. I mean, it's easy to say it wasn't hard when you're talking about it 20-something years later. But yeah.
Once you know how to do something, it's much easier.
But but it also didn't take that long time after it to be done. Yeah, no, but it was kind of done independently. There are a lot of names, but it's not really, there was that many cases. Yeah.
Sorry, silly question. Right, is there an algebraic way to see the associated Coxeter group of an Artin group?
Yeah, well, this is, if you just take this presentation and add relations that every generator's involution,
Okay.
that's exactly the presentation.
Okay.
Yeah, yeah. Yeah, so, okay, so this is linearity. Well, I guess it's kind of a natural question to also ask which, whether they're all linear. And there is a powerful method of proving linearity of groups, which is the whole theory of special cube complexes. So maybe I'll just write it as a sort of theorem. Jutta Haglund and Wise. So I'm not going to actually define special cube complexes because I'm not really going to use it so much in this talk, but it's this non-positively curved cube complex. It's some object you obtain from gluing cubes of arbitrary dimension, and there is for one, it has to be non-positively curved, which is some combinatorial condition, and there is some extra combinatorial condition. But let me just say that any group that can be realized as a fundamental group of such an object, so G is a fundamental group of a special cube complex, then kind of we get that it's a subgroup of S1C for some n, and so in particular it's linear. And so this is something, there's a lot more to this theory, but it's something that somehow is constructible, and there are methods of finding ways of representing various groups as special complexes. So this is definitely something that one can try to do. And we did. And so this is the theorem joined with Huang and Shatetsky in 2016 and independently by Patel. We showed that this is not very promising for Artin groups. We specifically, we were just looking at two-dimensional ones, or our methods work for two-dimensional ones. And I'm actually going to state it. Okay, maybe I'll just state it as.
Is it expected they're all linear?
What's that?
What is the status of the problem? The way you're writing it, do we know that, are we expecting them to be linear?
Well, we don't really know much more than those two.
That's all you know, okay.
There's no conflict.
No, and I would say that I think it's very I think it's likely that they might all be, but like, I mean,
Okay.
it's like, yeah, it's not. I don't think we have very good.
So it's possible they all linear anyway.
Yeah, it's possible. Yeah, it's definitely possible they all are. Yeah.
This method of proof that you're explaining. is-
Yeah, yeah.
Okay.
So, so this is of course like, it's not a question, like I'm not gonna tell you whether they're linear. I'm just gonna tell you that most, I'm using here kind of a little different words. Which, if you haven't seen match cube complexes, this might be a little confusing. I'm just saying, but so here the statement of the theorem, or like in a not very precise way, is that most two-dimensional free generator Artin groups cannot be represented as fundamental groups of compact, non-positively curved cube complexes. So in particular, special is like a more special version of these.
What do you mean? Most two-dimensional or three-dimensional?
And by most, I mean that we give full classification for those families. And
So this.
I can tell you exactly what it is. I
Tell
just,
us what the condition is, which must be satisfied to be negatively.
yeah, so there are obvious examples that are like right-angled Artin groups. So I guess,
Right.
for example, two-dimensional right-angled Artin groups. There is a little bit something that you can kind of add to them. So you can,
But what's the dimension again? What do you mean two-dimensional?
two-dimensional, it can be a homological dimension. But it's there, you can also state it in terms of defining graph, what is the condition to be two-dimensional, but it needs to be,
Okay.
or homological dimension at most two. But really, I'm going to focus for maybe most of my rest of my talk on just groups on free generators, because I guess I can say the most. So I'm just thinking I have three generators and I have, I guess 3 numbers that describe what kind of relations I have. And so here again, it's like almost all of them are not going to be fundamental groups of non-positively curved cube complexes. And it's, I think for a 3 generator is really the only example that is. It's like if you just take all the relations commuting and you get C cubed, which obviously is. Okay, so this didn't work, but I was able later to just address the question of residual finiteness for some of them.
Without showing they're linear.
Was that?
Without showing they're linear.
Yeah, without. So I'm gonna just write LMN. So this is gonna be just 3 generators where we have those 3 numbers describing the relations. So I was able to show that this is residually finite. When those numbers are any numbers other than possibly 2, 3, and some number. I don't claim that it's not residually finite in this case. I just couldn't do this case, but actually, since the case where the numbers are 2, 3, and even number, was done by my student, Grayson Mayer. I guess this is not yet an archive, but should be soon. And it's kind of interesting. I guess maybe I'll just for now say I'm not right now telling you much about methods, but I'm gonna just tell you that the same methods won't work for 2, 3, and odd. And this is due to a result by Wu and So it's kind of interesting to me that like there is something harder happening there. Yeah.
Your methods like really use that as 3, or is it also the case that you get like most of the cases of 4, but just was a longer list of counterexamples?
Yeah, no, so I get more, like I get kind of bigger family where it works, but it's like become, I wouldn't say that like it's a lot, like it's some condition, some kind of combinatorial condition that, I mean, I can tell you, but it's not that interesting on the graph, on the defining graph that has to be satisfied, which is not like, doesn't feel like super general condition.
Because it's not like the generic case.
Yeah,
If you're gonna explain the finite groups into which you'll explain this.
yeah, well, you mean like this? What is
Any of this, where you take your group and you're gonna find some finite quotients, which are you gonna somehow put your group,
Yeah.
find some representation into
Yeah.
a finite quotient?
Well, okay, so, well, I guess I can say a little bit of, so
Linear, we know how to
maybe
do it.
this is,
Reduce mod P. When it's non-linear, or when we know nothing, you have to tell us what your big trick is.
yeah, okay, so let me just say like very quickly right now. What is the proof strategy? Well, for most of those, there are some cases where it's a little different, or, well, yeah. So for most of those cases, what I actually show is that those groups virtually, so up to passing to finite index subgroup, split as what's called algebraically clean, which I'll describe in a moment, graphs of free groups.
Okay, I don't know what algebraically clean is, but I know how to do a free group.
So yeah, so graph of free groups, so maybe I should say finite rank free groups. And algebraically clean means that,
Also the edges, I mean, the edges are also.
yeah,
Write it down.
Okay, explain to us.
yeah, so yeah, okay. Okay, so maybe I should also explain what graph of groups is.
Yes, because I'm particularly interested in which groups, finite groups you land into.
Well, I don't actually know that. So, okay, so graph of groups is,
Let's start from
I mean-
the beginning. What's this ALMN?
No, that's
this is just a 3-generator Artin group. So it's I have just 3 generators and I have,
Yes, I just
for
wanted
each-
to make sure that.
yeah, thank you for clarifying. I just have 3 generators, each pair has LM or N, those 3 numbers. And so graph, I mean, so really maybe this here is gonna be the same if I just say that this is some free group with kind of, I don't know, what would be the notation with multiple agent and extensions. Do I need to explain that further? Okay, I think this is good enough. And this condition that it's algebraically clean means that those subgroups along which we do agent and extensions are, so edge groups are free factors in the vertex group. So they don't have to simultaneously be free factor in kind of one decomposition, but each of them is a free factor of the main group. So this is kind of the strat, like, well, this is, so maybe I should also right away say, I don't remember what year this is. Such graphs of groups are residually finite. And this really is not, it's not really very hard. So the hard part is to prove this statement. And so I can explain this. So just prove that Artin groups and free generators with 2, 3, and odd number never split as graphs of free groups. So without even looking at this algebraically clean condition.
But this, you got something when you're not 3, I assume. In some cases,
What's that?
this is almost a complete description for 3 generators. If you have more generators, then you've got just fewer cases.
Yeah,
that you understand.
So this kind of, this already said, like, for one, this already kind of forces group to be 2-dimensional. So this is kind of the only category where I can even ask this question, like whether this method works. But there is like further, and in fact, even, you know, what I'm telling you now here, it actually is not even something that I can do for all of them. I don't know whether all of them do virtually split as those, but like, I know that, yeah, there are some cases where I wasn't able to prove that, but I was able to kind of use slightly different. So there are few cases where I use slightly different method to get residual finiteness. Okay. Can you remind me what time I'm supposed to?
About 10 minutes left.
We have 10 minutes left. So. Okay, so maybe real quick without going into details, I'm gonna actually also state another theorem where it's joined with Kevin Schreve. We actually can also show that there is more than just residual finiteness. They're also virtually residually p-finite. And a good in the sense of SER or homologically good, or so I'm putting a lot of statements together. So I guess one is that they're also good. This is, so maybe I'll just write this without the P. This means that, can you see this color?
Yeah. Let's see.
Can you see this? Okay, so good means that if I look at the map from G to its profinite completion, which is profinite completion is just the inverse limit of finite portions of my group. There's always natural
Use
map.
white chalk.
What's that?
White chalk.
Okay. Well, I'm gonna leave this. So good means that this map induces an isomorphism on the homology. So if I take a homology with coefficients in any finite G module, I have the induced map. And being good means this is isomorphism. I mean, this is maybe a little bit mysterious object, because this is like a profinite group. But this you can think of as just a limit of okay. Sorry, I can't really see anything. Limit of finite quotients. So the same way as this is defined as inverse limit of finite quotients of G. I'm kind of looking at the cohomology of those finite quotients and taking the direct limit of that. So if, in other words, if the cohomology of this whole group can be kind of computed using the finite quotients, that's what it means to be good. And there is residually p-finite is the same definition of residually finite, but we're looking at only p quotients. And p good is kind of the p version of this. Just like one quick comment, we have virtually here, so we have to pass finite. Right, I also wanted to add for each p, virtually residually finite, there is something about ordering here that matters. I have to write p first and then virtually for our statement. This virtually is generally necessary because if you are residually p-finite for infinitely many primes, then it's a result of Rem-Tula that group is biorderable. Those groups are not biorderable unless they're right angle Artin groups. There's a slightly better versions that one can hope for here, but I don't know about it. Okay, so maybe in the last couple of minutes that I have left, I'll just give you a kind of baby example of this splitting. So I'm going to look at the group 2, 3, infinity. I said everything by 2, 3, and n, but 2, 3, infinity does not fit here. So this is an example where everything works, and it's kind of maybe the easiest example, I would say, where we know that this theorem applies, so that this is not a cubulated, it's not a pi1 of a compact non-positively curved special complex. So this is a group given by this presentation ABC, ABA equals BAB, and AC equals CA.
BAB.
Yeah, sorry. Thank you.
Infinity is odd or even? What did you say?
What's that?
Infinity is odd or even?
Is neither, or it's even, or I don't know. Yeah, this one is easy. This one does not belong to here. And you can actually rewrite this presentation slightly. I'm just going to replace one generator B by AB. And I can then write this first relation as AXA equals X squared. The second relation remains the same. And this is just because I want to draw you a picture of a presentation complex of this group. So this is a presentation complex. And I'm going to use blue. I apologize, Catherine.
But shouldn't you have the A on the flip? First in the left.
Yeah,
So
yeah, thank you. And to get a splitting of this group, we're going to consider certain subset of this. So I'm thinking of this as a two complex, so everything is glued together, all the AX and CR loops. So this is going to be one set. I'm going to consider another set, which is also this kind of horizontal set. I mean, in the perspective, that's how I write it. And so this is an open cover of the set. So we're using Van Kampen's theorem to get that this can be represented as pi1 of the set U, free product pi1 of V along their intersection. And if you look at those sets, how they're kind of built, you can see that this yellow set retracts onto, well, this X edge that I have at the bottom and top and C edge. So I have fundamental group of the yellow is fundamental group of this graph. Fundamental group of the blue is something that retracts onto graph that just cuts those two cells horizontally. So it intersects those edges at the midpoints of A. And so it has kind of two lobes with vertex at A. And then there is also their intersection, which can be viewed as this green graph that goes at this level, like 1/4 and 3/4. And So this is amalgamated along a graph that looks like this. And so this kind of naturally gives me free product with amalgamation of two copies of F2 along F3. And I guess I don't really have more time, but this is, I guess this is the single example where I could actually show you how to pass the finite index subgroup is index 6, where I can actually show you that it is, that it is algebraically clean.
So we
For
can
all other
ask him a
cases.
question for you to do that.
So for all other cases, I don't actually know. I don't actually even know how to, if in general, like I can prove that it always exists, but I don't construct it directly. All right, thank you.
If I gave you an element in the group and I said,
For this,
what's the smallest index, what's the smallest group in which it's non-trivially realized, you wouldn't even be able to give me an estimate?
for this one or for the other ones?
For your general theorem, typical one.
Yeah, I don't think I would be. Well, okay, so I don't think I would be. Like, what I use somewhere there is actually like the special complex stuff where.
Like which finite groups, you should be able to tell me which class, I mean, are you getting linear groups eventually? I guess every group is linear when it's finite, I guess, stupid question.
Yes. Oh, yeah, so. Okay, so maybe what definitely I can't tell you is how far do I have to go to get to this algebraically.
Or you can show me.
I guess once I have something that's algebraically clean, then I probably should be able to tell you, yeah. But like, so this is the part, this virtual is what I don't know if I can give you, like, I believe I don't know any estimate of like how far you would have to go.
Couldn't even sure that it's computable.
I mean, I haven't really thought about it very much, but I don't know how you would, and I feel like it's gonna be as hard as that question would be for generally, like if you have something virtually special, I think. I don't think it's an easy question of like telling you what is virtual to make it special. Like maybe there are some examples where it's known, but I think in general, that's a hard thing that it's not easy to tell. And I don't think there's a general, yeah.
Can you say a word about the two generators case? It's probably obvious, but.
Oh, yeah, for two generators, so, okay. What do you want to know?
I mean,
They're all, like, virtually, they're all, free groups times Z.
okay.
Or, I mean, unless it's Z squared, which I guess could be also free group times Z if Z is a free group.
Or it's a free group, which is a free group, not times Z.
Yeah. I guess, yeah. Yeah, so I mean, from point of view of like up to finite index, yeah, those are all free times C. It's two generators. Picture. Want me to draw the rest of the picture? Okay, so I'm gonna do it in two steps. So for one, when I have this thing, it's not, well, this group is always indexed, like this group is indexed to here. So I can kind of get rid of this by passing to index to subgroup. And so I would have something that I'm gonna use different colors now to encode things. I would have kind of two copies of those groups as an index to subgroup. And this graph in the middle, maybe I should use. maps over here as this kind of graph. This is everything you can kind of compute from this picture above. I'm just telling you that this is what it looks like. And I guess I would have to use another copy of this graph to draw you how it maps to the other side. But kind of the point is that the way, if you look at how this graph looks here, it might be not so hard to believe that if I now also pass to index 3 subgroup, I'm going to have something that this is a regular triple cover of this graph. So I'm going to have 2 copies of this graph as my vertex groups, and I would have 3 edges between them, where each of them looks something like that, but it's going to map to like in 3 different ways. So each I just have to map them in 2 different ways, so it's a little complicated to draw, but it's kind of like maybe this is mapping one direction and the other, it would have to be something that is slightly swapped. This is clean.